Now that we have some foundation in the theory of relativity, we can explore the consequences and really begin to understand what things are like near the event horizon of a black hole, where we have very, very strong gravity, meaning very, very strongly accelerated reference frames. Okay, so the key to the theory of relativity is what's happening with light. That's how Einstein made these discoveries, was by thinking about the path of light beams and what they mean and how people would observe them in different frames of reference. All the while maintaining the idea that the laws of physics have to be the same for everybody. And for that to be true, and for light to behave the way it apparently does, our conception of space and time had to be different. And so the way to think about that is gravity is actually going to curve the space around it. Because from our perspective, in whatever reference frame we happen to be in, light travels in a straight line. However, in a different frame of reference, looking at that path of light, it will have traveled a curved path. But the light isn't traveling a curved path in its own reference frame, it's traveling in a straight line, but the space that it's in is curved. And so we're transitioning from one idea about gravity where it is that matter is pulling on each other, and there's this invisible force in between them, to now thinking about gravity totally differently, that massive objects deform the space around them, and things are just traveling along in that deformed space. Okay, so let's try to understand this in the context of an example. So let's think about a light beam on a spaceship. So we're going to imagine shining a laser from the back towards the front of a spaceship. It will make a straight line path towards the front. However, let's assume that the spaceship is in an orbit, right? It's traveling around the Earth in an orbit. Well, in order for it to leave the back of the space shuttle and hit the front of the space shuttle, it would have to follow the same trajectory as the space shuttle, which we know is in orbit. And that means the light beam would have to essentially be in orbit. It would have to curve to hit the front of the space shuttle, as viewed from, let's say, Earth. As viewed from the space shuttle, it just travels in a straight line from front to back. Okay. So the key here is that light is going to be in free fall also. When we say that free fall is the same as zero gravity, that also applies to light. And in Newton's theory of gravity, light was not involved. Light did not get pulled by gravity because light doesn't have mass. Einstein's theory of gravity now includes light. So light can be pulled by gravity because it's not an invisible force doing the pulling. It's actually the matter deforming the space around it, and light is just traveling on that deformed space. So we can think of the Earth sitting at the center, and the space around the Earth is curved in such a way that the objects around it are just sort of swirling around the perimeter of a bowl. And light is no different. Light will also swirl around the perimeter of that bowl. Okay, a better analogy to think about that is that space is like a rubber sheet. And so imagine we are like the ant on a rubber sheet, and we're traveling from one side to the next. This would be like flat space. We would think of this as flat space. There's no objects in here, there's no stars, and so we can just travel from one place to the next in this straight line. But if you put a massive object on the rubber sheet, the rubber will stretch, and now the space is curved. In order to go from here to here, the ant has to travel down and then back up and then across. So essentially, this is what matter is doing to the space around it, sort of pulling the space down like a rubber sheet and curving the space around it. So if we compare how different objects deform the space around them, the sun would cause a dent like this. A white dwarf, which is as massive as the sun but smaller, would have more gravity, meaning a more strongly curved space. So it's like stretching the fabric of space, the rubber sheet, down even further. Neutron star even further because it's more densely compacted. And then the black hole is the extreme, where it essentially falls off to nowhere. And there's some imaginary line beyond which light can't escape because it's so strongly deformed that light can never make its way back up. You'd have to be going too fast in order to get back out of the tunnel. So everything from here up can get out, everything from here down cannot. Okay, now keep in mind that these are sort of projections of what the space would look like around these objects. But the objects are actually three-dimensional, and we're just drawing them as two-dimensional. So they're circles, right? The sun is just a circle on here. We can't really draw what it's really like, which is three-dimensionally curved space. But essentially what we're seeing here is any slice of space that you wanted to look at would be curved in this way. Okay. So then we should ask, how do we know that the theory is correct? The mathematics that was worked out by Einstein and others to take advantage of this equivalence principle, apply this equivalence principle, reveals these details about space being curved. But how do we know that that theory is correct? Well, one way would be to see an effect of gravity on light, because Newtonian gravity does not include any effect on light. If we can see an effect on light, then we can confirm the theory of general relativity, Einstein's theory of gravity. And so the first test of that was something known as gravitational lensing. All right, so we can illustrate that here in this diagram. We have the Earth, we have the sun, and now we're viewing the sun as deforming the space around it, curving the space around it. So if there's a distant star behind the sun, the light from that star would travel along a straight line, but then it would encounter the curved space around the sun, and that would lead it to bend in a new direction, and it would be deflected to the Earth. Okay, now if that star was really behind the sun, and Newton was right, completely right about gravity, then we would never see that star because the light would travel, and either hit the sun, or it would travel above the sun and would never make it down to the Earth. It would just continue in a straight line, right? Light doesn't have matter. It would not be affected by the sun's gravity. It would just continue in a straight line past the Earth, and we'd never see the light from that star. However, if Einstein is right about gravity, then the light from that star will be bent by the sun in a new direction and will head towards the Earth, and we would see it. And we would project that starlight to have come from this direction. This would be the apparent direction to the star. So in 1918, Arthur Eddington was able to measure the deflection of light from stars behind the sun during an eclipse. The only time this was going to be possible would be during a solar eclipse, because even if the light from this star was deflected and getting here on Earth, we wouldn't have this sensitivity to see it because the sunlight would be so bright that the sky is too bright and we wouldn't see any stars. We don't see stars during daytime, but we can see stars during daytime during a solar eclipse. So he timed this, so he had his equipment ready I believe, don't quote me on this, but I believe it was somewhere in Africa he went and set up his his experiment to make a picture, a photographic image of the night sky during the eclipse, and then compare it to star charts. And he saw a star here that was deflected by about 1.75 arc seconds from where it should have been, which was a direct confirmation of the theory of general relativity. And so from that point forward, it was no longer debatable that now we have a new theory of gravity. General relativity, matter curves the space around it. Okay. Now, space gets curved and time slows down in strong gravity. So we need to explain what that means. What does it mean to say time is very slow? We did get into that a little bit in the special theory of relativity. When things are moving fast relative to what they're measuring, time slows down. But time also slows down near strong gravity sources. And this is something a little bit different. The first one, the special relativity case, is called time dilation. This is called a gravitational redshift. And it's called that because of the way that light gets affected by gravity. The light is a wave. Waves have a frequency, right? How often the wave crests pass you by. If time slows down, that frequency gets slower. And if frequency gets slower, the wavelength has to get longer, because remember, the speed of light has to stay the same. So the waves get stretched out, meaning they move towards the red end of the spectrum. So we call the time dilation that's due to gravity a gravitational redshift. Okay, but essentially what's happening is that anything in the presence of strong gravity in very curved space, the more curved the space is, the slower the clocks run. This is, again, something that's been tested, and not only has it been tested, it's essential for us in our modern day lives. I imagine you are like me, and you depend on your car's maps to get you wherever you want to go. And those rely on GPS satellites, and those GPS satellites are depending on Einstein's theory of general relativity to get the clocks synced up correctly. Because those satellites are in a weaker gravity than we are, our clocks down here on Earth run slower than the clocks up in orbit. And in order that the signals match up, essentially the GPS is measuring distances to things by sending signals back and forth, and the timing of those signals allows it to calculate the distance. So it needs to understand, or the software that programs them needs to understand the gravitational redshift in order to get precise timing, in order to measure precise distances. And so we have many, many now confirmations that time runs slower in gravitational fields. So the stronger gravity is, the slower the clocks run. The more curved the space is, the slower the clocks run. Okay, so now let's finally think about the black hole itself. As you approach the event horizon of a black hole, you're entering very, very curved space where time is going to run very, very slow. At the event horizon, what happens? Well, we've mentioned that the event horizon is where the escape velocity is equal to the speed of light. Essentially, at that point, space is curved so much that light can't escape. But another way to look at that is, at that point, the dilation of time, the gravitational redshift, becomes infinite. So the frequency of light waves becomes infinitely long. And so another way to think of that is that time is essentially stopping at the event horizon. Okay, so you're far away from the horizon, your clock's running perfectly normally. You're near the horizon, your clock's running perfectly normally. The laws of physics are still the same in those different locations. However, when you compare one frame to the next, when you make a comparison, like say, how long did this event take to happen, there'll be dramatic disagreements because the person who's in the strong gravitational field near the event horizon would have their clocks running much, much, much slower. And the formula here calculates exactly how much gravitational redshift there is. For the mathematics of black holes can be very, very complex. And essentially, what we've learned over the course of many years of studying theoretically the theory of relativity and black holes specifically is that black holes depend on three properties: their mass, their spin rate, and their charge. So the formula here is if you have the blandest of possible black holes, so with no electrical charge and it's not spinning at all. So you just have a mass collapsed down beyond its event horizon. In that case, this formula will tell you how much time dilation there is, how much gravitational redshift. On the left-hand side, this is the time measured by the observer that's near the black hole, and this is the time for an observer that's infinitely far away. So the symbol for infinity means that you're infinitely far away from the black hole. Basically, you're in space that's not curved at all. And then there's this term here, which is a square root 1 minus the Schwarzschild radius divided by the radius of the observer. So depending on how far you are from the black hole. Now, r can never be less than rs, because if r was less than rs, this number would be bigger than 1, and you'd be taking the square root of a negative, which you can't do. So the formula doesn't work for inside the black hole. At the Schwarzschild radius, at the event horizon, r is equal to rs. This is 1. 1 minus 1 is 0. And the time between events is 0. So time is stopped when you're at the Schwarzschild radius. And then as r gets bigger and bigger and bigger, eventually imagine this number gets, very, very big. So this number is basically 0. You're really, really far away from the black hole. Then 1 minus 0 is still 1. Square root of 1 is 1. And then the times match up at that case. All right, so that formula will help us calculate that. Okay, so let's do one quick example. Suppose you had lunch by a black hole. So you take your spaceship, you want to go see what it looks like, and you go to a distance of 1.1 times its Schwarzschild radius, so about 10% beyond its Schwarzschild radius. And then you are there for an hour. So in your clock, remember, everything in your frame of reference is normal. And so you have a timer, and in an hour you head home. Well, how much time will have elapsed for the people back home? Because you were in a presence of strong gravity, your time was dilated. We can plug in the numbers into this formula to figure out the conversion between the two reference frames. So far away, 1 hour is the time where you were near the black hole. TE, I put it as TE because this would be the time back home on Earth. And then we have the R is the 1.1 times the Schwarzschild radius. Now, I write it like that because then the RS's cancel, and we just have numbers to deal with. You plug in those numbers and solve for TE. It turns out it's 3.3 hours. So what you experienced as 1 hour, everyone back on Earth experienced as 3.3 hours. The closer you get to the black hole, the more extreme that difference is. When you watch, if you for the movie watching assignment, if you choose to watch Interstellar, they travel to places where there's strong gravity, and they get this time dilation, and they get it more extreme than even this. I forget the exact discrepancy, but the idea there is basically the same. They go on to a planet that's near a black hole where the space is very dramatically curved. The gravitational redshift applies, time gets dilated. So comparing the clocks there to the clocks back home on Earth, and you get this huge discrepancy. So like 30 years goes by when only an hour goes by for the people in that strong gravity. Okay, now the last thing I want to say about the theory of relativity and black holes in general is that we've had another recent confirmation of one of the predictions of this. And this might actually open up a whole new way of studying the universe. So let me back up for a second and remind ourselves that everything that we learn about astronomy learn from the observations of electromagnetic radiation. You know, we have to see what's out there and let that light come into us, and then we can dissect it and figure out what it came from. Well, there might be another thing that we can get information from, and that directly comes out of the general theory of relativity. And that's that because matter curves space, when that matter moves around in space, it creates ripple in the fabric of space and time. And those ripples travel outwards at the speed of light, it turns out. And so if we can record those ripples, that will tell us about the matter that was moving. And they've been long predicted by Einstein. So talking about like almost 100 years of thinking about these things before we had built a detector sensitive enough to actually measure them, measure these gravitational waves. And the first were detected in 2015, and it a few years ago won the Nobel Prize. The team that put together this experiment won the Nobel Prize in physics for this discovery. And the facility, one of the facilities, there are multiple facilities. One of them looks like this. They're all built sort of similarly. They're essentially long beams where they have one beam going in this direction and one beam going in this direction. And the idea is that as a gravitational wave comes through, it will stretch the space, and you'll see slight changes in the lengths of either this pipeline or this pipeline as measured by the lasers going back and forth. And I believe that these things are something like a mile long, and they can measure changes like the width of a proton by the sensitivity of their laser measurements. And so if a gravitational wave comes through, it will stretch and compress the space in a certain way, and that will create little differences, which they measure as the strain on the pipeline, and they'll get some sort of pattern. But in order for this to happen, you have to have a pretty big event. And so the event that was recorded in 2015 is believed to have been a merger of two black holes. So two black holes in space came in close enough contact that they began to orbit around one another and then spiral in and eventually collide. And all three of their different setups measured the same signal, so they had direct confirmation. And the pattern of wiggles, which just might look like random noise to you, this exact pattern of wiggles with these, so you can sort of see it gets further apart and then closer together as the amplitude grows. This exact pattern was predicted by the theory of relativity with very, very high precision. And they were able to tell from this pattern of wiggles that what happened in space was something like this, the collision of two black holes, and they could even estimate the sizes of those black holes. So we now have multiple confirmations of the theory of general relativity. It's one of the most successful theories that we have, and so our thinking about stars, and this especially as you get close to stars, has to include the effects of general relativity. That these massive, compact objects like white dwarfs, neutron stars, black holes, the way that they curve space leads to changes in how we measure time, how we measure distances. And they also can create ripples that emanate out into space. And so maybe going forward, we can learn about things as our detectors become more and more sensitive. We can learn about things not just from their electromagnetic waves, but also from their gravitational waves. And so this may open up an entirely new way of studying the universe, and who knows what new mysteries it will present to us and what old mysteries it will help us to solve.